Okay, welcome everyone. Today this is the Dynamics of Robot Mechanisms course, and today we will talk about closed kinematic loops, structures again. Please ask if something is not clear, and you can make notes. I think it helps a lot in the understanding of the material. So we should take a short reminder before we start everything. So the structure of the semester so far was like there was a first part about the basic or fundamental definitions about mechanisms. It was long ago at the beginning of this semester, and here we were talking about some analysis techniques and also design techniques. And then we were talking about open loop kinematic structures. Such as the arm and most of the industrial robots, and we were addressing the kinematic analysis and kinematic equations. And the other thing was to construct the dynamic equations. And basically the homework is about this part. And we were also talking about some control issues. A very basic motion control technique was introduced. So this is what we have so far. And this will be the new part. I will switch to some different color. So now we are moving on with closed loop structures. Closed loop structures, and in this semester we will talk about only the kinematic analysis of closed loop structures. And dynamic will be in some other subject in the MSc courses. And we will talk about a graphical approach, a geometric approach, which only works for planar mechanisms, but later also in MSc courses we will talk about some kinematic analysis techniques which works for spatial rigid bodies, and there are no restrictions. Okay, so this is the last thing which we will talk about today and next week. So let's go with the kinematic analysis of closed loop structures. I think we were already talking about the closed loop structures. So open loop means that the links are just coming after each other, and there is there was a definition. If you want to go from AI to J, for example, there is only one possible route to get there. Okay, this is the open loop kinematic structure, and it is also called serial structure, and closed loop structures are also called parallel structures. And here there are two or more possible ways to go from a certain link to another link. For example, we have this mechanism. For example, two open loop robots are grasping the same object somewhere, and if you want to go from here to here, from link I to link J, then you can go this way, or you can also go this way, and both are possible, so it is a closed loop structure clearly. And what we are talking about today is applicable also for closed loop structures, and of course for open loop structures too. So usually the methods that work for closed loop structure, they are also applicable for open loop structures. And as we said, we will addressing some geometric or graphical approach, and it is based on the so-called instantaneous center of velocity. So that's a reminder at the beginning. So let's talk about the instantaneous center of velocity, which is the sebességpólus in Hungarian language. And if we talk about instantaneous center of velocity, we have to say that it does make sense only in case of planar motion. So the first thing what we should define is the planar motion itself. So now we will restrict ourselves only for planar motion, and the definition was that the motion is planar if it is always true that the angular velocity of any rigid body is perpendicular to any velocity vector. For example, if I have a rigid body here and I have the angular velocity vector, and this is vertical, it means that each point has a velocity vector which is in the horizontal plane, and it is true for each point of this rigid body. Okay, so this is the planar motion, and of course this is angular velocity, and this is the velocity of point A. So this is the first thing what we have to remember. If this is true, then we are talking about planar motion. And let's move forward with the definition of the instantaneous center of velocity. In Hungarian, this is the póluspont. And let's have a graph. So let's say we have a frame which is fixed. Let's say this is x and y, it doesn't actually matter, but the important thing that this is a fixed frame, it is not moving. And we said that there is a rigid body moving here, and the rigid body has a certain point, for example A, and it has a velocity VA, and it has also an angular velocity which is perpendicular to this plane. And we said that there is always a certain point of which the velocity is 0. So we said that this is a vector from A to P, and P is the instantaneous center of velocity. So this is basically a point somewhere in the plane, and we said that the velocity of point P is 0, and this is important, that point P is always a different point. So if I calculate the position of point P, I can say that the velocity of this point is 0 only in this particular time instant, and in, let's say, 1 second later there will be another instantaneous center of velocity. So P will be somewhere else usually. So we can only say that the velocity of point P is 0 in a particular time instant. And this is called instantaneous center of velocity. And we say that the velocity is 0. So basically what we do here is to compare the velocities to a fixed frame, and this will be different later when we will talk about relative instantaneous center of velocities. And the question is how to calculate this point. So you can use different approaches to determine the position of point P, and we will address 3 different approaches to calculate the position of point P. So one approach is to say that the velocity of point P, which is 0, can be calculated by the formula VA plus the angular velocity cross the vector from A to P. Okay, so this formula is true, and we said that the velocity of point P is 0, so therefore we have an equation for this unknown vector. Okay, so this is unknown, we would like to calculate this, and if you try to solve this equation, finally you will obtain some formula. RAP is equal to, let's check it and don't is equal to the angular velocity cross product with VA over the square of the angular velocity. So one option is just purely calculate the position of this vector, and then everything is nice. But we should know that there are some physical meanings of the instantaneous center of velocity. So there is another calculation technique which is basically graphical. So let's say the input data are the angular velocity and the velocity of point A. Okay, so let's say the input data are the angular velocity and the velocity of point A, and then you can create a construction. So let's say this is the rigid body, this is VA, and this is A, and we say that this is an instantaneous center of velocity because it seems that in this particular time instant the rigid body is rotating about point P. Okay, but this is only true in this particular time instant. So the rigid body is rotating about P in this particular time instant, about P in a particular time instant. So it rotates about point P, but at the next time instant P will be somewhere, so the rigid body will rotate about a different point. But now it's rotating about P, and if it is rotating about P, then you know that the center of rotation should be somewhere in the line which is perpendicular to point A. So this is a perpendicular here, and P must be somewhere in this line, but you don't know where it is, but you can calculate the distance. So it can be also in this side or that side. We can determine this later. And you also know the distance from point A. So this distance here or this distance here is equal to this term, the absolute value of the velocity over the angular velocity. So it will give you a meter. This is the radius, and this is the same here. And how do you decide whether it rotates about this point or this point? You just clearly see it from the figure. So if this rigid body is rotating about this point like this, then the velocity would be in the opposite direction. So this is not possible. Okay, but if this rigid body is rotating about this point P, then the velocity of point A will be really in that direction, so it really works. So you know the direction of this line on which the point P is situated, you know the distance from point A, and by just looking the figure and trying this rotation thing, you can decide which side is the real location of point P. And there is a third calculation technique when I will just put it here. So the input data can be the velocity direction of two different points. For example, if there is a bar which slides down on a wall, but it continuously touching the ground and the wall too, then you know that the velocity must be tangential to the ground here. This is VA, let's say, this is point A, this is point B, and VB also tangential to the surface. So this is VA here, and you use the first idea what was also used here. So the instantaneous center of velocity must be on this perpendicular line, but this is also true for the other velocities, so it must be also in this line, and it should be on both lines. So finally the intersection of these two lines gives you the position of the instantaneous center of velocity. So these are three different techniques how to calculate it. These have a message on the level of formulae. This is a message that point P is rotating about some point instantaneously only, and this also has a physical view of the whole thing. So it was just a reminder, and now we can move on the relative instantaneous center of velocities, which will be used for the analysis of the motion of planar mechanisms. So the next step is to move and understand what is instantaneous center of velocity. But in the terms relative. Okay, so relative instantaneous center of velocity is the next thing what we address, and basically the idea is exactly the same what we have here, but instead of comparing the velocity of point P with a fixed frame, we will compare the velocity with another moving rigid body. So we will basically just change this word into something else. So our figure will be a bit similar. So this is the moving rigid body with point A, and there is also the velocity vector of point A, and instead of this fixed frame I will draw another rigid body which is also moving, and in this rigid body there will be another point of which there is also a velocity vector. So we have to define the whole velocity state of the body. So this is the angular velocity for the first rigid body, and this is the angular velocity for the second rigid body. So what we know everything about their motion, and instead of comparing the point where the velocity of rigid body number 1 is 0, we are looking for the point where the velocities of the two rigid bodies are equal to each other, and this will be our definition for the relative instantaneous center of velocity, and the indexing will be 1 and 2 because it should contain the index of the two rigid bodies, of which this is the relative instantaneous center of velocity. Okay, so P is the relative instantaneous center of velocity, and the definition is that this is the point where the velocity of rigid body number 1 and 2 are equal to each other. This is the point where the velocity or velocities of rigid bodies 1 and 2 are equal to each other. So graphically I would draw something. It don't have to be necessarily in the overlap of the two rigid bodies. It can be actually anywhere in the plane. It can be also in infinite distance if the rigid body is not rotating at all. But that's also a possible case. So let's say this is P12 here, and this is the vector from A to P1, 2, and this is another position vector from B to P12, and we state that this point always exists, but it can be checked if we create some similar equations than before. So by definition, based on our definition, we can create the equation which is identical with this statement. So we said that the velocity of point P12 is equal to VA plus omega 1 cross the position vector from A to P. So this is the velocity of point P12 calculated based on the velocity and angular velocity of rigid body number 1, and I can do the same calculation by taking into account the velocity and the angular velocity of the second rigid body. So this is, this should be omega 1, yeah, and then I do the same with the second rigid body. And I arrive to an equation where there are a lot of unknowns, unfortunately. So this is unknown, and this is also unknown, right? And this means that all in all we have two equations, because this is a scalar, this is a vector equation in the plane. So this is two scalar equations. And we have two vectors in the plane, so we have four scalar unknowns, which is not good. But we also have some position level information, because we are aware of this vector which gives us, so this is a known information, because I know everything about the rigid bodies and their motion and their position. So this vector which goes from A to B is also known. So if I just change, for example, this vector and I express it with the other two vectors, then we will have something useful. So VA plus omega 1 cross RAP12 equals to VB plus omega 2 cross, and this vector should be expressed by these two vectors, and I think it will be equal to RAP21 or 12 RAP12 minus RAB, which is not unknown, this is given. And then we reduced the number of unknowns to 2. Okay, so this is the only unknown in this equation, and we will be able to calculate it always. So we don't prove it, but it's always possible to calculate it. Maybe this point will be in infinity, it doesn't matter, but we can achieve the result. So this is basically two equations and two unknowns. So we can calculate it. Two equations, two unknowns. So finally we can calculate. And this is the definition for the relative instantaneous center of velocity, or in Hungarian, relatív pólus. And we will use this for our kinematic analysis. But before, let's check a very simple example, just to see how it looks like, just to have a feeling about it. So let's consider a train, and the train is moving on a railway. There are a lot of wheels, and in the train there is also something which is moving. So this is the floor of the train. This is a cross section, okay. And on the floor of the train there is another small car. So now it's not typical. Maybe in international trains you can find it, but sometimes there's a guy who sells food and drink for people, and the food and drink is served in this small car. Okay, so food inside. And let's draw some relative instantaneous center of velocities. But if you want to do that, we have to use some numbering. I will use different color for the numbering. So the railway itself is number 0. This is fixed to the earth. And let's say that this wheel is rigid body number 1, this wheel is rigid body number 2, the train, the car of the train is rigid body number 3, for example, and this wheel, let's say, is rigid body number 4, and the small car is rigid body number 5. And of course there are a lot of other rigid bodies, but we are not able to draw each instantaneous center of velocity, because we will see later that there are a lot of them. And basically, just to understand what it means, we can draw P10 or 01 here, because in this point the wheel is touching the railway, so the velocity must be equal to each other in this point. And actually, if the railway is a fixed coordinate, is a fixed frame, then basically it really equals to the, so it is the same as the absolute instantaneous center of velocity of the first rigid body. But here there is a real relative instantaneous center of velocity. So this point is P13, because in the bearing or the axis of the wheel, the velocity in the center of the wheel, the velocity of the wheel is equal to the velocity of the car of the train. So in this point their velocity is equal to each other, so therefore it is a relative instantaneous velocity. And this is the same here. So this point is P23, because here the center of the wheel has the same velocity as the train. And let's draw some other points. So here, where the small car touches the floor of the train, the velocities are also equal to each other. So this is the relative instantaneous velocity for the rigid body number 3, which is the car, and the wheel. Oops, sorry, there is no numbering for this wheel, so I have to do the same for the front wheel. Okay, so here the train and the wheel number 4 has the same velocity. So this is, for example, an instantaneous center of velocity. And let's draw another one in the center of the same wheel. There is P45, because the velocity of the wheel in the center is equal to to the velocity of this car in which there is the food. Okay, so you can see that if there are a lot of bodies, then you will find a lot of instantaneous center of velocities. And there is one thing what you probably recognize, that I always use the smaller number first and then I have the larger number. So this is also important, that Pij is identical to Pji. It is very similar to the shear stress in strength of material. Tau xy is exactly equal to tau yx. This is the same here, so there is no sense in distinguishing P3, 4 and P4, 3, so they are the same. Okay, it is very, very important. And let's calculate the maximum number of, or the number of relative poles. Okay, so we already see that there are a lot, but how many do we have? That's a big question, but it leads to the field of combinatorics. So the question is, how many instantaneous, how many relative instantaneous center of velocity do we have? That's a big question. But as you see, this is the same problem as calculating the handshakes in a group of people, and the solution may be familiar from some probability mathematics subjects or something. So the number of the relative instantaneous center of velocity will be equal to n choose k, or in Hungarian n alatt a k. So these are the so-called binomial coefficients. And in general, the calculation of this formula is that first k should be addressed. So I start with k and I multiply with k minus 1 and then k minus 2 until I reach 1. And in the denominator I will start with n. I will multiply it with n minus 1, n minus 2 until I reach n minus k plus 1. Or in other words, I would say that I have the same terms up here as many terms I have down here. Okay, so we will see later how this formula looks like. Okay, so these are the well-known binomial coefficients, or we could say n choose k. This is how to say this thing. And now if we apply this, it could be proven, but yeah, it's quite trivial. So we can pair them in the way when finally n will be equal to the number of rigid bodies. So n equals to t. This is the number of rigid links or rigid bodies. in other words links, and instead of k we will write 2, because 2 rigid bodies are taking part in creating a pair. Okay, so that's why it is 2. So finally the number of instantaneous relative poles will be equal to T over 2, and the formula will be, and I will perform the same thing again. So if k is 2, then I start with 2 and go back until I reach 1. So this is 2 times 1, and up here we have t times t minus 1, and now I basically have the same number of terms up here than I have down there. Okay, so finally we would say this is 1 over 2 times t minus 1. Sorry, t times t minus 1. Okay, so this is the number of relative instantaneous central velocities, and let's check how many do we have in some certain amount of rigid links. So for example, if I have one single rigid body, so t equals to 1, I have one single rigid body, then it will be equal to 1 times 1 minus 1, which is 0, over, it doesn't matter what. So finally it turns out that there is no relative poles, but this is trivial, because if there is just one single body, it cannot make a pair with any other rigid body, so it's quite trivial. And let's see the next example. If we have two rigid bodies, then t is equal to 2, and then 2 times 1 over 2 is 1. Okay, so if we have two rigid bodies, then they can make a pair, but there are no more options. And finally the instantaneous center of velocity will be somewhere. Okay, we will only have one. And let's consider another example. So if I have 3 rigid links, let's check the formula. So t is 3, 3 times 2 is 6, over 2 is 3 again. So the number of instantaneous center of velocities is 3. So we can draw 3 of them. This is P1, 2, P2, 3, and there is P1, 3 somewhere. So you can combine the indexes in every possible way, except changing the order of the same indices. That's not good. And we also can calculate, but we don't create a drawing. So if we have 4 rigid body, then the instantaneous center of velocities will be 6. So this is the 4th example. So as you can see, it grows in a quite high rate. So by increasing the number of rigid bodies, it's growing up or blowing up. The number of instantaneous center of velocities is blowing up. But the thing is that we are able to calculate the number of them. I hope everything is clear so far, because now we are going to move on the theory which will be useful in the kinematic analysis of planar mechanisms. So let's move to the so-called Aronhold-Kennedy theorem. Okay, Aronhold-Kennedy theorem. And it will talk about the case when we have three rigid bodies. Okay, so the Aronhold-Kennedy theorem considers this case when we have three rigid bodies, and it purely says that if it can be included into the theorem. So if we have T equals to 3 rigid bodies, then there are 3 instantaneous center velocities and they will be collinear, and that's the important part of this statement, and they are collinear, which means that they are situated in a straight line. They are situated in a straight line. This is the meaning of collinear. So it was not unintentional, or I could say it was intentional, to draw these 3 points on a straight line, because it could be proven that they are always situated on the same line if we have 3 rigid bodies, or if I have more rigid bodies but I choose 3 of them and I create their relative instantaneous center of velocities, they will be situated on the same straight line. And this is the Aronhold-Kennedy theorem itself, and we will be able to use it. But before that, let's calculate the number of these straight lines. So this line is called Aronhold-Kennedy line. This is the last part of this theorem. So this line is called Aronhold-Kennedy line. And let's calculate how many of them do we have. And we will have a formula for the number of them. The number of Aronhold-Kennedy lines will be n, the notation will be nk, like Kennedy. So it will be T over 3. This is a binomial coefficient again. And T over 3 means if I start at the beginning, at the bottom, sorry, it will be 3 times 2 times 1. And here I will have T minus 1, and t minus 2. So this is how it computed the number of Kennedy lines, and after reorganizing this formula, this will give us t times t minus 1 times t minus 2 over 6. Okay, so this is the formula to calculate the number of Kennedy lines. And now we create again our examples. Okay, it's better to start from the beginning. So again, we can consider one single rigid body. This formula will give us a 0, because if I substitute 1, then it will be 0 because of this term. Okay, if I have two rigid bodies, sorry, t here is equal to 1. If I have two rigid bodies, t will be equal to 2, and the number of Kennedy lines will be still 0 because of this term here. So if t equals to 2, then 2 minus 2 is 0, so this whole term will be 0. So there is one relative pole, but there is no any line which can be fit on this one single point uniquely. So therefore it doesn't work. And if I have 3 rigid links, then t equals to 3. As we mentioned, the number of relative poles will be 3, and the number of Kennedy lines will be equal to, and this is 3 times 2 times 1, it is 6 over 6, which is just simply 1. And this is really working. So there will be 3 points which are relative poles, and there will be one single Kennedy line which can be constructed, and it goes through all of the 3 points. And here we can consider the last case, when we have 4 rigid bodies. Somehow they are arranged in the space or in the plane, and that's important. So here t equals to 4, and 4 times 3 is very much, 12 times 2 is 24. 24 over 6 is, I think, 4. No, it should be 3. 24 over, let's calculate it again. So it should be 3, but how it happens? So it's 4 times 3 times 2 over 6. No, it's correct. Yeah, it will be 4. Okay, and I think it will be visible in the drawing, because we also should calculate the number of relative poles, NP, which was equal to 4 times 3 over 2, which is equal to 6. So the number of relative poles will be 6, and this is really true, because we will be able to create 4 Kennedy lines, and there will be, later we will see how it works. So I will be able to create 4 Kennedy lines. Okay, and because of the Aronhold-Kennedy theorem, in each intersection of these lines there must be one single relative pole, and together we have 6 relative poles, and we have 1, 2, 3, 4, 5, 4. 1, 2, 3, 4, yeah, Kennedy lines. I hope it's understandable. This is a quite important drawing here. but we will see some examples. The examples will even more clear, will make even more clear everything. If there are some questions, please ask. And let's move to some examples. So I hope everything is understandable here. So we can calculate the number of relative poles, the number of Kennedy lines, and we also have this statement, and the most important part is this one. The three relative poles are collinear, so they are situated on a single straight line. And let's apply this for some mechanical problems. Okay. So let's take an example of a 2 degree of freedom robotic arm, for example. Degree of freedom robotic arm. So what we have is that there is the first rigid link of the robot, which is fixed to the ground directly, and there will be another link which is fixed to the first one with a revolute joint, so it can rotate, and we can also show the numbering. So this is link number 1. The ground is also a rigid body, so this is link number 0, and this will be link number 2. And the question is that we should determine the position of the instantaneous center of velocities. So the question is, where are the relative instantaneous center of velocities? And we can try to find it, and we'll see how many or what kind of informations we will need. So let's try to solve it. First, we should calculate the number of relative poles and the number of Kennedy lines. So we have 1, 2, 3 rigid links. So T equals to 3. We have 3. This is the simplest case when we can apply the Aronhold-Kennedy theorem. And based on the number of rigid links, we can calculate the number of relative poles. So this will be 3 times 2 over 2, which is 3. We will have 3 relative poles, and we also can calculate the number of Kennedy lines. We already done it. So this is 3 times 2 times 1 over, it was what was it, over 6, which is 1. Okay, so we already know the number of points which are the relative center of velocities, and we can make an attempt to draw them. So there are some trivial poles, so that's the next step, to define the position, and we will collect some of them which are trivial, so we just use it in this course, but we mean that they are very easy to find that. Naturally, this point will be P01 because here the two rigid bodies are joined together, so the velocity must be equal to each other. And basically this is also equal to the net relative but absolute instantaneous center of velocity for the first rigid body, because the velocity of the ground is zero, so the ground is a fixed object. And then we can define this point, which is P12, because here link number 1 and link number 2 has the same velocity because they are attached to each other here. So we can call like that. P01 and P12 was trivial. And the other one, the third one, should be found by using this Aronhold-Kennedy theorem. Aronhold-Kennedy theorem helps us to find P02, which is basically the absolute instantaneous center of velocity for rigid body number 2. So we can find the pole, velocity pole, or in Hungarian the Póluspont, the absolute instantaneous center of velocity of rigid body 2, if we find this P02 relative instantaneous center of velocity. And what we know is that there is a line here. The things which are coming from the Aronhold-Kennedy theorem will be, for example, green. Okay, so we use the Aronhold-Kennedy theorem. So this line is coming from the Aronhold-Kennedy theorem, and this is the Kennedy line. And now we will see how to denote it. So this will be Kennedy line, and we will collect all of the indexes here, so 0, 1 and 2, and these are the indexes of the rigid links, of which this is the common Kennedy line. It is a very trivial case because we have only 3 rigid links, but this is the Kennedy line, and based on the Kennedy theorem we know that these 2 points should be on this line, and therefore the third one should be also on this line. So the information what we have is that P02 must be on this line 2. Okay, so this is the information what we know. But unfortunately we don't know anything else, so we need some extra information, and I will just draw it right now. Let's say that we know the velocity of this target point or tool center point, for example. Okay, let's say I know the velocity vector of this point. Okay, so the input data are the configuration of the robot, and also the direction of the tool center point velocity. This is the velocity vector basically. And now we can put together everything. So we know that this P02 must be on this line. This comes from the Aronhold-Kennedy theorem. We also know that since 0 is fixed, P02 is identical with the real center of velocity of this rigid body number 2, and we also know that what we have seen at the very beginning of this class, that the absolute instantaneous center of velocity must be on a line which is perpendicular to a velocity of which we know the direction. Okay, so we know the direction of this velocity, and we also know that the P2 must be on this line, so finally, when these two lines are crossing each other, we will find the point PO2, which is identical to P2. Okay, so this is how it works. It's a bit complicated because we need a lot of different things. We know we also have to use the Aronhold-Kennedy theorem. We also use this perpendicular construction line, and we also know that if rigid body number 0 is fixed, then these are identical to each other. But still, I hope it was understandable. And let's take a look on a very similar, different problem. Please ask if something is not clear here. So let's check another problem, which will be the wheel of a steam engine. So this is the railway itself. This is rigid body number 0. This is the railway on which the train rolls. There will be a wheel. This is the wheel of the steam engine. This is a driven wheel. This will be rigid body number 1. This is the wheel, which is a driven wheel. Okay, that's important. And in the case of steam engines, the wheel is driven by a bar which connects to the cylinder where there is the steam itself. I have to remove this stuff from here. Okay, so there is a cylinder in which we have a high pressure steam, and then this bar will transfer the force onto the wheel, and therefore the wheel will exert a torque, and the train will start to move. And this transmission bar, let's say, or transmission rod, it doesn't matter. This is rigid body number 2. And again, the question is to find the relative poles. Okay, that's the question. Where are the poles or relative instantaneous center of velocities? And let's collect all of the information. And again, we start with the trivial things. So trivially, we find P1, which is identical to P01, because this is the relative pole of rigid body number 0 and 1, and this is exactly the same as the pole of rigid body number 1. So this is P1, which is identical to P01. And the other thing, what we know is that rigid body 2 and 1 are fixed together here with a bearing. So this is P12. P12 is also trivial to find. And again, with the Aronhold-Kennedy, we can find P02, which is actually the same as P2. This is the instantaneous center of velocity of rigid body number 2, or the relative instantaneous center of velocity of rigid body number 0 and 2. And again, we should collect everything what we know. Here, this is a line. Now I switch on red. This is a line which is a Kennedy line. Because we already know that P1, P01 and P12 should be on a Kennedy line, and the line is K01 and 2, and the trick is the same again. So we know that the velocity must be horizontal. So this is the velocity of this point. Let's say this point is A. So this point is VA. And again, we use the same trick. So here the velocity is known, and I can construct this perpendicular line because I know that the absolute instantaneous center of velocity P2 must be somewhere on this line, and we also know that it also must be on the Kennedy line. So finally we find this point. Okay, so here we say P2 must be on this line, and in the Kennedy line we know that P02 must be on it somewhere. Okay, and in the intersection we can realize that P2, which is identical to P02, is in the intersection of these two lines. Okay, so this is again another example where the Aronhold-Kennedy theorem was applied. And now we still don't do any kinematic analysis. After this it would be possible. So now I could calculate the velocity of each point of this bar if I want, or anything else, but that will come later. Now we will just working with the Aronhold-Kennedy theorem itself. And let's see so next week we will go one step forward, and then we will apply it for really calculating velocities and angular velocities of the rigid bodies which take part in the mechanism. I hope it was understandable. I'm just checking if there are some questions or not. And let's see the last example. It will be a 4-bar mechanism, so we will add one more rigid body, and we will have more than one Kennedy lines, and that will be the point where we stop for today, because now we will realize that if there are more than 3 rigid bodies, it can be quite complicated to manage so many relative instantaneous velocity center points. So next week we will find out some algorithmic ways to manage them. So the last example for today is a 4-bar mechanism. It is a really closed loop mechanism, and again the task will be to find all of the relative instantaneous center of velocities intentionally drawing these bars in this tilted position. Otherwise I will not have enough space in the whiteboard. Okay, so this is our 4-bar mechanism, and let's use some numbering. The ground is rigid body 0 again, and this is number 1, 2 and 3 moving link. So again we can collect our parameters. So the number of links is 4 now, and then we can compute the number of relative poles. We already done it. It will be 6 if we use the formula, and we also can compute the number of Kennedy lines, which is 4 if we use the formula. And the task is to find the relative poles and the Kennedy lines. Okay, so find them. That's the task. And the solution is similar as before. So first we collect the trivial poles. So this is trivially here because 0 and rigid body number 1 are joined to each other here, are joining with the bearing. So this is the relative pole of rigid body number 0 and 1, but number 0 is fixed again, so it is identical to the absolute pole of rigid body number 1. And this is the case here, where rigid body number 3 is fixed to the ground. So usually, by the way, the goal is to find these absolute instantaneous center of velocities, but the relative poles can help us, as we will see now. So the trivial is P01, which is identical to P1, P03, which is identical to P3, and what else? We also have some points here and here in which the velocity of rigid body number 1 and 2 are identical. So P12 is here and P23 is here, P12 is here, and P23 is also here in the group of trivial poles. And by using the Aronhold-Kennedy theorem, we have to find the missing relative poles, which are P, and we don't have, for example, P02, right? It's missing from here. And we also don't have yet the P13, and basically this is identical to P2. So it would be very nice to find the instantaneous center of velocity for rigid body number 2, because then the velocity analysis would be possible in a simple graphical way. So that's the benefit. And now we should apply the Aronhold-Kennedy theorem. So here we can construct all of the Kennedy lines, Aronhold-Kennedy lines. So this horizontal line is Kennedy line 0, 1 and 3, because I'm just collecting the indexes of all rigid bodies. And this line here is the Kennedy line for, again, we collect the indexes 0, 1 and 2. And we can also determine the position and orientation of this line which is the Kennedy line 0, 2, 3. And we said that there are 4 Kennedy lines, so there should be one more, and it will be collinear with these 2 points. And this line is Kennedy line 1, 2, and 3 based on the figure. And now we can use the Aronhold-Kennedy theorem again to find these points. So the information what we have is that P02 is on every Kennedy line where its index appears. So it should be on Kennedy line 1, 2, 3, and it should also appear on Kennedy line what did I say? 1, 2, 3. Okay, let's go back a bit. It will be too quick. So PO's based on the Kennedy theorem, PO2 is collinear with based on the theorem with P01, P12. So this will be Kennedy line 0, 1, and 2. Because this forms a Kennedy line based on rigid body number 0, number 1, and number 2. But it is also collinear with P01 and the P03, which is basically Kennedy line 0, 1, 3. Because there is rigid body number sorry, yeah, it will be, I was just mixed up the whole thing, so now it's clear. So P02 must be also collinear with point 03 and 0 and 2, 3, because rigid bodies number 0, 2, and 3 are forming a group of 3 rigid bodies. So based on this information, we know that P03 must be on this line, and it should be also in 0, 2, 3, so it should be also on this line. So finally the intersection point is somewhere up here, and this is exactly the same as the absolute instantaneous center of velocity of ring number 2. And based on the same thinking, the pole 1, 3, which is still missing, is collinear with 2 lines or 2 points or 2 sets of 2 points. So it is collinear with P01 and P03, because rigid bodies number 0, number 1, and number 3 can form a group, and the corresponding Kennedy line is 0, 1, 3. So 0, 1, 3 is this, so P13 should be somewhere on this line. And the other thing is that we can create another grouping, so rigid bodies 1, 3 and number 2 can form a group, so we can also say that P12 and P32 should be collinear also with P13, and the corresponding Kennedy line is 1, 2, 3. So 1, 2, 3 is here, so we know that P13 is on this line. So the idea here is that we have a lot of rigid bodies. If we go back here, so if I'm trying to find P00, then I say that okay, rigid body number 0 and rigid body number 2 is in the group of the 3 rings, and we can choose another link into the group of the 3 links. For example, we can include also rigid body number 1, or I can form a separate group with 3 links in which there is link number 0, 2 and 3. And based on this extra information, I will have 2 crossing lines, and the intersection point will give us the instantaneous relative center of velocity. And we have done the same here, so P13 is corresponding to rigid body number 1 and 3, and in the group of 3 rigid bodies we can also include rigid body number 0 or rigid body number 2, so we can actually highlight the extra rigid body which is included in the group. So here P10, so this is the extra rigid body which is included in the group, and here this is the extra rigid body which is included in the group. And if I have 3 rigid bodies, then I can construct the Kennedy lines. Okay, so based on every information what we have, we can say that this is P10, which is basically not an absolute instantaneous center of velocity, just a relative one. But here we obtained some information about the absolute instantaneous center of velocity of rigid body number 2. So now what we will do next time, if we know that there is an angular velocity, an input, or it should be positive, this is an input motion, and I know that this is the pole of rigid body number 1, then I know that the velocity will be something like this, and each point can be calculated here. And then I can do the same for this rigid body, so here it's perpendicular to the bar, because this is the center of velocity, and again each point can be calculated, and it is easy. But I can do the same for the rigid body number 2, because I know that this is the center of velocity. So here, if I construct a perpendicular line, I will see that this is the velocity of this point, and this is the velocity of the other endpoint, but any other point can be calculated. So here the velocity is something like this, here the velocity, and this is perpendicular of course, here the velocity of something like this, and so on. So I'm always able to calculate any velocity on the rigid body, and okay, we can include another point here. Okay, so that's the benefit. After you have find the absolute center of velocity, then you can easily calculate a lot of things. Okay, so and actually also can calculate the angular velocity if I consider this length and this velocity, or this length compared to this velocity, so everything will be easy after this point. So thank you very much for today. I just check if there are some questions or not. I don't see any questions, so we will meet next week, and we will continue on with this graphical method. and then this is the end of the semester. So goodbye for today.